meter. It's the other way around. Okay, so 1 meter equals to 10 to the 9 nanometer. So this is the wavelength, and when you do this calculation, dimensional analysis, nanometer cancels out. Okay, times the n known, the frequency equals to 2.998 times 10 to the 8 meter per second. So meter and meter cancels out from each side of the equation there, and then this number divided by 532 over 10 to the 9. Okay, so that's 5.32 times 10 to the negative 7. Okay, you put that number in here and you do the calculation. This is the frequency. So using this equation, we need you to be able to do calculation. Many of the homework questions there for the first learning objective ask you to, given the frequency, ask you to calculate the wavelength, given the wavelength, ask you to calculate the frequency. So this equation is something that we need you to remember. Okay, punch in the number, make sure you get the correct answer. And when the nanometer, when the wavelength is in nanometer, you're going to end up with a very high frequency. Okay, so basically in this case, when we're looking at the electromagnetic spectrum, this is something that I need you to pay attention on the sequence of the electromagnetic spectrum. When you saw in the video there, and say starting with a very short wavelength of gamma rays, going all the way to very long wavelength of radio waves. Okay, so the radio waves on the left of this picture there, radio wave has long wavelength, short frequency, a very low frequency. Okay, and gamma ray has a very short wavelength, extremely high frequency. Now we need you to remember that frequency and wavelength are inversely proportional. Frequency times wavelength give you the speed of light. So in this case, if you have very short wavelength, very high frequency, it also has something to do with the amount of energy that it carries. And when you go to the X-rays there, you see the technician put you in a room and put the instrument around you. They leave the room. Why? Because they work in there day in, day out. The radiation X-ray carries a lot of energy. They don't want to be exposed. And you are only there for 2 seconds taking a picture, and a brief exposure to the X-ray is okay. We can tolerate that kind of exposure. But the technicians work there, and the medical personnel, they work there day in, day out. They need to make sure that they are not exposed to a high dose of radiation there, because they carry a lot of energy and can do harm to your health. Now, what I need you to pay attention to is the sequence of the entire electromagnetic spectrum. Going from long wavelength to short wavelength, you have radio, microwave, infrared, visible, and then ultraviolet, X-ray, gamma. Those are the regions there. Now, gamma rays, and they have different frequencies there, different types of gamma rays there. As long as the frequency is between 10 to the negative 16 to 10 to the negative 11, that's a very, talking about the wavelength. And the wavelength between 10 to the negative 15 to 10 to the negative 11, all of that wavelength belongs to gamma ray. And in terms of frequency, that's 10 to the positive 24th, all the way to somewhere around 10 to the 19th, 10 to the 20th. Okay, I don't need you to memorize all these numbers there, but I need you to know the sequence and pay special attention to this particular section of the electromagnetic spectrum. This is everything that human eye can see. We call it visible spectrum. Visible spectrum starts with 750 nanometer in wavelength to 400 nanometer in wavelength. Different colors are exhibited in this particular region. So if I ask you, giving you a list of radiation, ask you which one has a shorter wavelength than the visible spectrum, well, you got to know what are the radiations on the right side of the visible spectrum, because these are the radiations with a shorter wavelength, higher frequency. These are the radiations with longer wavelength and lower frequency compared to the visible spectrum. So this is something that you need to. One of the things that I use the M word, something that You need to remember the sequence of the electromagnetic spectrum there, going either from radio to gamma ray or gamma ray to radio. The correct sequence. Very important. You gotta remember this. Okay. Another video very quickly talking about the EMR spectrum, also on YouTube. I'm watching a lot of YouTube videos.
The electromagnetic spectrum, an immense scale used to measure the wavelengths of all kinds of radiation. At one end are radio waves with the longest wavelengths. At the other end are gamma rays with the shortest. In between are the other bands, including visible light, which is such a tiny fraction of the whole, it's difficult to imagine. How small is the visible spectrum? If you had a reel of movie film representing the entire electromagnetic spectrum, stretching 2,500 miles from California to Alaska, the section containing the visible spectrum would fall somewhere in the middle, near the University of Washington.
This frame is the whole visible spectrum. It is one frame and over 2,000 miles of tape. It's everything that the human eye can see. The importance of this frame is that stars emit almost all of their light in this part of the spectrum.
And even though the light is visible, it still contains hidden tools. The secrets are in the spectrum itself. The visible light in this lamp comes from hydrogen gas excited by electricity to form a glowing plasma, similar to what happens in a nebula. By viewing the lamp through a diffraction grating, we can split the light up into 3 narrow lines on the spectrum, a virtual fingerprint of light, unique to hydrogen alone.
So in the spectrum, you see 3 features. One is red, one is a light blue, and the other is a deep blue. This pattern of wavelengths is absolutely unique to hydrogen. And there's no way to confuse hydrogen in the spectrum with any other element.
Now, talking about that, we're getting into the topic of line emission spectrum, okay? And we'll look at that. And again, but before we get into that, look at this equation. The first equation that we need you to remember and be able to use to do calculations. And this is the relationship between the wavelength and the frequency. Okay, and then this equation, we give you multiple homework questions and even quizzes on the third quiz there, asking you to use this equation to do the calculation there. So make sure you remember this equation. You don't have to memorize this number. I'll give you this number, but you just need to understand the relationship between the wavelength and frequency. They're inversely proportional to one another. Okay, and again, going back to the start of the quantum mechanics there, and the quantum revolution there, is that around the turn of last century, in 1900 there, scientists understand that matters consist of small particles, atoms, protons, and neutrons, and electrons. Okay, and then electromagnetic radiation carries energy. Okay, and they consist of magnetic waves, wave factor,